Hello guys, in this video I would like to explain different normality tests in R. In the previous video we explained the normality test in Python, and we have talked about the regression, and not particularly about regression but background of the test. So you can see the video on which is the link is given in the description of this video, so you're going to go and you can see the video. That was in Python, and maybe some of you're using R and maybe not familiar with the Python. So I decided to do the same video side by side in R and Python. So today I will explain all the three tests: Anderson-Darling test, Shapiro-Wilk test, and Jarque-Bera test. These all tests you can use for to test the normality of the data. So we will do this in R today. In the two tests, I mean that all these tests have the hypothesis that the data is coming from normal distribution. You can Google and you can see the detail. So this means that the null hypothesis is the data is normally distributed. So then you will see your test statistic for Anderson-Darling. You need to compare your value of the test statistic with the critical values, and for Shapiro-Wilk and Jarque-Bera test you need to decide based on the p-value. These tests are useful when you are dealing with the regression modeling, time series modeling, or any other type of data analysis. Particularly, I'm talking about regression time series modeling because these models have the assumption of normality, that the data is normally distributed with certain mean and standard deviation values. So before embarking on modeling using these techniques, you need to check whether the data is normally distributed or not. If the data is not normally distributed and still you are using these approaches, the results may be misleading. So it is really important to check the data, and if the data is not normally distributed, then it's fine if it is normally distributed. But if it is not normally distributed, you need to use some transformation like square root transformation, inverse transformation, log transformation, and Box-Cox transformation. We will talk sometime about the transformation as well. Okay, let's move toward R, that how you can do these tests in R. So this is my R studio. And the first one is Anderson-Darling test library nor test. You need to install this if you don't if you don't already install it. And this I already call it, but you need to call library nor test. And then initially I need to generate two data sets. One is normal data set and the other is skew data set. Remember the description is given here. Generate 100 random number from a normal distribution. This is the first data, and data underscore normal. This is stored in this one. Okay. And now this is data is skewed, and this is chi-square distribution. This is RCHQ from chi-square distribution with degree of freedom 2. So you can go back and you can see what is chi-square distribution. Maybe sometime I will do a video on this as well. Generate 100 number random number from chi-square distribution. So two data set, and we will apply each test to each of these data set, and you will see the results. Okay, so now let's generate this data. Just run this command so that we can have the same data. Okay, now this is the first data normal, then the skew data. And now you need to apply this test. I think these tests look easier than the Python. In Python, the things are different, but they have their own advantages and merits, and R have their own advantages and merits. So you can use any one of them, which one you like. The main thing is you need a data analysis to get some information from the data science, machine learning. Yes. Okay, so I'm just applying now from the Anderson-Darling test for normal data. This is just for normal data for the first data, and I need to write data normal. I need to write this one here because this is only data. This will not work with this. This will work if the data exists already, but okay. So now run this. The result is stored here, and now you can print the result, or you can just write the result. You will see the results. So this is the results, and this is the test statistic, and this is the p-value. The p-value is 0.9104. What is mean by this? In case of 95%, I can, in case of 5% level of significance, if the p-value is greater than 0.05, we accept the null hypothesis that the data is normally distributed. So this is 0.910. This is very high, very, very high. So this means that of course we accept the null hypothesis that the data is normally distributed. As you can see, the null hypothesis I did not mention here, but okay, and somewhere I mentioned here the null hypothesis, and as that you can Google it. Just want to see, yeah. So you can see that the null hypothesis is that the data are normally distributed. So this is for Anderson-Darling test, and I mentioned for the remaining two in the R script. So this means that, and of course, because we generate this data from normal distribution, so this is normal distributed. Of course, the p-value is so high. This is the reason. If you have your own data, maybe the p-value is, the data is not normally distributed, less than 0.02 even. Okay, so you should take care about this, and you can read the data in the CSV, from the CSV or from the online sources, as we already talked about this. Okay, so this was the random, the normal data, so the p-value is too high. But remember that you need, yes, so this is the p-value. Okay, this is yes. In some cases, like in Python, if you remember, we compared the test statistic with the critical values. So in that case, perhaps Python was unable to calculate the p-value, but in R you have p-value, so easy to interpret the result. You don't need to compare the value of the test statistic with the critical values like we have done in Python like this. These are the critical values. So of course that is 0.1. This is at 15%. And if you compare that statistic value, that is 0.1, very less. This is 0.1 at 0. So this is of course accept. And we accept the null hypothesis that the data is normally distributed. Now do this. For the skew data, the second data which we generate from chi-square distribution, just click, run this. Okay, yeah, we don't have this data, but we just need to see this one. Okay, actually we don't have the data object. Here the data was mentioned, but we don't have the data object. We have the skew data, so the result are stored in results. Just print it and you will see. Yes, now you can see the p-value because we generate the data from skewed distribution that was not normally distributed, and the p-value is very, very less, 5.135 raised to the power minus 12. In that case, we reject the null hypothesis and conclude that the data is not normally distributed. We need a transformation to make it normal if we are using technique which required normality of the data. So this is all about Anderson-Darling test by using two data sets. One is normally distributed and the other is skew data. So you can check and you can practice and you can use your own data instead of these data. This is just for for explaining these tests. Now let's come to the Shapiro-Wilk test. Again, the same data I'm using in all the three tests: data normal, data skewed. So Shapiro-Wilk test, this is also a test which is normally used for normality test. And just click. So Shapiro test, the result are stored here, and just if you write this, you will see the result. But if you print, then also you can get this. So this is the test statistic, and the p-value is 0.9349, just like the Anderson-Darling test. And of course, why not? Because the data we have drawn from normal distribution. So the null hypothesis here is Again, the data is normally distributed, so we accept the null hypothesis the data is normally distributed. Now apply the same test to skew data, and if you want to make the difference, just write SK. The result will be stored in Shapiro_test SK just to make the difference. And now just write this. Remember, you need to write SK here, otherwise you will print this result which is different. Yes, because the data is not normally distributed, it's from the skew distribution. So the p-value is 3.993 raised to the power minus 9. Very less. So again, the same thing. We have proven the same thing, that for first case, the data was normally distributed, so the p-value is 0.9, very high. Second case, the data is not normally distributed, so the p-value is very less. Now add the Jarque-Bera test. For this you need this library if you install. This is normally used in time series data analysis, so that's why t-series, and I installed already, so I can call it just by using this command. Then the hypothesis that the data is normally distributed. And now for normal data, this is the command for the, if you see the command for Anderson-Darling test is ad.test, and for Shapiro-Wilk test, Shapiro.test, and for Jarque-Bera test is Jarque-Bera, Jarque.Bera.test. So this is the function you need to remember, or you can get from internet. Of course you need. And JB test normal, JB test skewed. Okay, so this is for the normal data. Just need to apply and you'll store the result in JB_test_normal. Now print the results. Yes, the p-value is again very high, and that's 0.9189. So this means that of course we accept the hypothesis in this case as well. Jarque-Bera test. Apply to the skew data now and print the result of the skew data. Yeah, of course, this is again very low p-values. There are differences in the p-value for the skew data, but yeah, every test give us the same result, that the first data is normally distributed and the second data is not normally distributed. So in today's video, we have learned that how we can apply 3 tests: normality test, Anderson-Darling test, Shapiro-Wilk test, and Jarque-Bera test for testing normality of the data in R. So I think this is enough for today. And if you are interested in Python, the link is given in the description of this video. The same thing I have done in Python, and this is in R. So thank you very much, and see you in the next video. Ciao.